In this lecture, we're going to start talking about some of the applications of radiochemistry. And we'll go through a few different examples of this. And in this first video, I want to talk about, I'm going to focus on I'm going to focus on radiometric dating. So here's a big list, though. Here's a lot of isotopes that we use in our lives. Everything from smoke detectors to pest control to preservation of food and labeling different atoms within chemical reactions to study them, which I'm going to highlight that one just because that's one I've actually done and I like. Hey. We also do this to analyze things through neutron activation analysis, so we can chemically analyze. We authenticate art objects. We use it in crime scene investigations. We use it to measure the thickness of things to see how much a particle will actually get through. And we use it in agriculture, in nonstick pan coatings, and photocopiers, and cosmetics. It's just there's like a lot of things we use it for, and we're not going to be able to learn about all of them. So we're going to focus on medical applications, and on radiometric dating. So looking at radiometric dating, what is that? So it is looking at the rate of decay of a radioactive nuclide that's constant. And so we can compare the amount of a nuclide in something with what it would have been at the point of like death or an object at a certain amount of time. So we use it to look at the age of an object, and we can look at the amount of like the isotope it decays to. We can look at what's remaining, and so if we think about looking at things that are really, really old, we use for geological dating, we can look at volcanic rocks and the dates of the date of the Earth and things like that. We're going to use things that have really long half-lives, like uranium-238 or lead-206. And using that, we're able to figure out that the Earth is somewhere between 4 and 4.5 billion years old. And then in the same fashion, we use carbon dating to determine the age of a fossil. And so carbon-14 is radioactive. It's got a long half-life of 5,730 years. And within our planet, where the atmosphere is constantly making new carbon-14. And so while you're alive and you're exhaling CO2 and inhaling oxygen, you are always going to be replacing carbon-14 in your body with more carbon-14 from the air, from carbon dioxide. And so while you're alive and breathing, you're constantly replenishing that carbon-14 concentration in your body. But that stops when you stop breathing. And so then you can actually date fossils and determine, based on the amount of carbon-14 left in the fossil, when it stopped breathing. So we can go back as old as 50,000 years. Just fascinating, I think. The looking at the half-life, if we think about this in time and percentage of carbon-14 left. So if we're going to look at an organism dying, that's when our carbon-14 decay begins. And it's going to be on the scale of a half-life of over 5,000 years. We're going to compare the ratio of carbon-14 to carbon-12 in the fossil to something that is a living organism right now. And so we can detect this as long as we keep, we can detect it below 6 half-lives. So we get down below 1% of carbon-14 remaining relative to the percent that would be in a living organism. And so that allows us to date things. So let's just do a quick calculation example on this. So this is really similar to the half-life problems we were doing because it's just a half-life problem. And these are all first order. So they're more straightforward. The thing about this problem that I think is the oddest is the units. Dis per minute gram C, right? What is that? So this is really a measure of radioactive activity. And so what it is it's the dis is disintegration. So things breaking down per minute per gram of carbon. All right, and so this is looking at rate rather than the number of particles for radioactivity. And so what we'll do is we'll use our, instead of capturing this as like number of radioactive particles, we'll capture it as the rate of decay or the rate of disintegration per minute per gram of carbon at a specific time versus the initial rate. And that'll be equal to our KT. Negative KT, sorry. And so what we have here is our current and our living organism and our fossil, essentially, to compare. And so the initial one, that 0, that's going to be the living organism. And the one at time t, however much time has passed, will be our fossil. And so we are going to need to find t, which means we really need K as well. And so that K is going to come from our half-life equation for first order. And so we're going to need to use the half-life of carbon-14 because we're doing radiocarbon dating. So that half-life of carbon-14 is 5,730 years. All right, so let's plug this in. So let's start with our half-life equation and using that to calculate K. So our rate constant is going to be equal to 0.693 divided by that 5,730 years. And that's going to give us a value that is 0.1824 days, years. Sorry, I'm looking at the wrong one. 1 point is far off. Looked at the wrong part of the page. 1.209 times 10 to the negative fourth inverse years. So now we can plug that K value into our integrated rate law, and we're going to solve for time. And so plugging in, we've got our natural log of our fossils rate, which is 4.5 disintegrations per minute per gram of carbon, divided by something that's living, which is 15.3 disintegrations per minute per gram of carbon. And we're going to then divide that by our rate constant K that we just calculated 1.209 times 10 to the negative fourth inverse years, to give us our time, which that has passed since this fossil stopped breathing. And that value is going to be 1.01 times 10 to the fourth years. So it's pretty old. So given that, it's just like our half-life problems we were doing before. It's just we know the half-life is always going to be for carbon-14.